All right, we are recording now. Let me go over one or two kind of minor announcements. I already talked some of this over with Clark. Friday was a pretty good day in the office on the Birmingham campus last Friday. What made it pretty good was a couple things made it pretty good. Now, this sounds really bad, but I was the only one there. So there were few distractions. Other people did come by, and stuff, but by and large, I could get a fair amount done. The dean canceled the meeting she had scheduled for Friday, right before a 3-day weekend. Smart move, I thought. So I got quite a bit of grading done. Whittled down the stack significantly. Didn't get it finished, but got quite a bit done. And then, over the weekend, I only had little bits here and there on Saturday, Sunday, because we had a lot of things to catch up to do. But then Monday, as Clark and I were talking, turned out to be such a rainy, miserable day that I had most of the afternoon, well, a good portion of the afternoon, to grade papers. So I got the stack whittled even further, significantly far. And now, since I've been back yesterday and the day, I've got piles more coming in, so I'm back, not as bad as I was, but still behind. But my red ink pen ran out sometime Monday afternoon when I've been doing all that grading. I could not find another one in the house. I couldn't find it, so I thought, well, I'll quit looking and just start putting grades in Blackboard. So I did finally get your Blackboard caught up. Thought I got everybody caught up, but then realized yesterday when I said that to my first class that I skipped their class and the 113 class. They didn't have that much to do, but I should have gotten those done too. So I'm still behind on Blackboard, but not for this class. So anyway, then the other thing is sort of a good news, bad news situation. Next week is Thanksgiving week. That's the good news. The bad news is there are no classes at all next week. Okay, get over it. Okay, I bet you UAB still has classes, don't they? Yeah. Okay. But we, the two-year college system has our annual meeting actually Sunday, Monday, and Tuesday. Sunday evening, Monday and Tuesday, always of Thanksgiving week. So classes don't meet at all the week of Thanksgiving. We'll be in meetings. Those of us not going to Mobile, which I cannot see any point in going down to one of those meetings in Mobile, and we don't have the budget for it anyway, we'll be having professional development here. So a couple of issues with that then are, number one, the college is open Monday and Tuesday of next week, and Wednesday. Technically, it's open Wednesday too. So if you have any business to do with the college, you can get it done. There will be somebody in all the major offices, okay? Probably not a full staff, but somebody in all the major offices, okay? Faculty, those that are not at the meetings in Mobile, will be on campus on Monday and Tuesday, but we will be in meetings. And always in the past, and I think it'll be this time too, we'll be over on the Birmingham West campus, okay? So I will not be in this office at all. Yes, sir.
Fire drill postponed.
Again, okay.
Well,
I don't blame them. I'm glad they did.
Yeah, so y'all have to go out and do the fire. You were aware of it, right?
No, I haven't seen the email. But
yeah, postponed then too.
Okay, good. Okay, thank you.
See you.
Day like today, that would be miserable. Okay. All right. But though we'll be on campus, those of us who don't go to the meetings will still be in other meetings. We'll be in meetings on campus. So I won't be available to get to by phone or in the office or anything else, especially Monday and Tuesday. Wednesday, they usually give us that as an office day. So I should be in the office Wednesday. Now, which office, I'm not sure. I'm guessing here on Bessemer, but in case something comes up that I need to be on Birmingham, I may be there. So try calling first before you come. And if you don't get an answer, don't leave a message, Because on this one, I'm not sure my voicemail works. On that one, it's somebody else's voicemail. So don't leave a message, but wait a few minutes and try back, 10 to 15 minutes, call again. And both numbers, and then see if I'm there. If I am, I'll let you know. Now, here's the thing about Wednesday, though. It's never guaranteed, so we can't count on it. But most of the Wednesdays before Thanksgiving, the holiday weekend coming up, they usually let people go a little early. How early is hard to say, okay? Depends on who the administrator is or what he had for supper that night. Or I don't know what it was. But sometimes it's been 2 o'clock. I think I can remember at least 1 o'clock. It seems like I can remember one that we left at noon, but there's no guarantee. But here's the deal. If you have business to take care of at the college, Monday and Tuesday, guaranteed the office will be open all day. Wednesday, not guaranteed. I can almost assure you it'll be open in the morning. I don't know how long in the afternoon they'll be open. So if you've got business to do with the college, get it done Monday, Tuesday, or Wednesday morning. Don't wait till Wednesday afternoon because you might wind up being disappointed and find out they closed 15 minutes ago or something like that. So try to get it done Monday, Tuesday, or Wednesday morning. Okay. And then to catch me, the best chance will be sometime Wednesday, but try both offices before you make a trip. Okay. Any questions? Either about that or about what we're going to be doing here. So I need to load you up with stuff so you won't be bored with. You just missed a Monday class and now you're missing a whole week of class. This is awful. I apologize. I wish we could have done something about it. Huh?
As a millennial, I'm offended.
You're offended? Okay. Sorry. Okay. As soon as you said you're millennial, I just tuned the rest of it out. I'm just kidding. I'm just kidding. Okay. Sort of. Okay. This, I think, is where we left off last time. It's on page 488 in your text, Chapter 7, Applications of Integration. 7.5 is work. Okay? This is the bottom part of the page, 488. What we were doing was talking about different ways to integrate and find forces or work when it's not constant force in a constant direction. Okay? If that's what you got, constant force in constant direction, its work is equal force times that direction, as long as they're in the same direction. Okay. The first type that we had was if you have a variable force that depends on where you're located to be that, then typically your delta W, the incremental part of the work that you do, is the force times the incremental displacement. Okay? That's one way. Another way to formulate the increment of work is the force increment times the distance. If the so you can do either one of those. The second interpretation of delta W is useful in problems involving the movement of non-rigid substances such as fluids and chains, things like that. Then you vary your force, the delta force. You do increments of the force, especially if you're moving these in, say, a given direction. Okay? So that's the two ways to do your integrable force work. Okay? So here's example 4. This is the top of page 489. A spherical tank of radius 8 feet is half full of oil that weighs 50 pounds per cubic foot. Find the work required to pump all of the oil out through a hole at the top of the tank. Let's see if they have a picture. Yeah, there it is. Okay. So you're going out. You can almost picture this as being the big peach down in Clanton the water thing, that's pretty much a spherical tank. They added a little stuff to make it look like a peach, except it's not filled with oil. Okay, hopefully. Okay, that should be water in there. Okay, so here's what we've got: a spherical tank, exactly half full of oil, and you're going to pump it out through the hole at the top. And they also told you it's a radius of 8 feet. Okay, and that the oil weighs 50 pounds per cubic feet. That's your weight density. Okay, so how you need to set this up, and I sort of wish I could have drawn this rather than depending on them because they have too much of it here already. What you do is imagine a little increment of this thickness here, and you're going to figure the amount of work it needed to pump that out. Other words, lift a thing. So they picked an increment down here, a delta y here. So they're doing the first way of doing that, the force times the increment in your displacement. Okay? So what we have to do, if we're going to delta y, we have to get everything in terms of y. Okay? Your force is going to be the weight of that, which is going to be 50 pounds per cubic feet per cubic foot. So you're going to have to determine the cubic feet of oil in this little delta y here. Okay? That's one of the things you got to do. This is the density, okay? But you got to get the volume of that. Because volume times density would be weight density would be weight. And that would be the amount of force you need to apply to that delta y. So the first thing you need to do, or one thing you need to do, is, well, probably the first thing you need to do is set up your coordinate system where it's going to work the best. Okay? So I think it makes perfect sense to have the y-axis going through the sphere like this, from top to bottom, right down the middle. That's your y-axis. Now, where to put the x-axis? And I guess it's sort of up to you. They put it down here at the base, which I think makes good sense because then you're integrating from a positive number. If you put it here, then your y's are all going to be, you have to adjust for that. So I guess it makes good sense to put it at the base down here. Okay? So your y is the distance from the south pole down here of your tank to this increment here. So that's going to be your y. Okay? The thickness of that is your delta y. Okay? Now, your x then, because you did choose this right down the center of that, the axis of that sphere, then your x is going to be how far out here on y you're going. Okay? Now that introduces an x that you really don't need because you got delta y's, y's, you know, everything's in terms of y. So you need to figure out what this x is in terms of y. And that's where the good old Pythagorean theorem comes into play. And probably the best way to picture this, and actually that may not be a bad color, but I think we probably do need to get a darker color. Okay, if you let this be your radius, because the tank is exactly half full, okay? So there's your radius, okay? And this place down here is here, and this comes up to some point there, okay? That's a pretty ugly picture, but this then turns out being your x here. This, of course, if that's the radius, that's going to be 8 feet, okay? Now, this distance down here is y, remember, up to this band that you got going through there. So the distance here has to be 8 minus y, right? Okay? then your x here, this distance from here to there, is the square root. X is equal to the square root of 64 minus, okay, this thing squared, right? That length right there squared. Got it? So what is that? This is 64 minus 16y plus y squared. Just squaring that, right? And if you do 64 minus 64, the 64's go away, okay? So that's handy. And then what you have left is, I'm going to rearrange the order here, y squared minus 16y. So that's what your x is there. Okay, square root of y squared minus 16y. Now why did we need that? Okay, because that's the radius of your slice there that you've got this delta y of thickness. Okay, what are we going to do with that? Well, the volume of oil in that slice is going to be the area of the slice, which is pi. The area of this slice right here is going to be pi. Area is equal to, let's call that a delta area. Okay, it's going to be pi times that radius squared, x squared, so that's going to be times y squared minus 16y, right? Okay, because you squared it. Okay, the delta V is going to be this times your delta y. That slice of area times the delta y. So it'll be that area times your thickness, delta y. So that gives you your volume. Multiply your volume in cubic feet by pounds per cubic feet, so you have a 50 out front. That gives you the incremental force. That's your delta F. Is this thing right here. Okay. Now, that's your force, the weight of the oil that you're pumping, right? That slice of oil right there, that is it. This is its weight. It's 50 pi y squared minus 16y times delta y. Okay? Your thickness times your area times your density. Okay? That gives you how much weight of oil you have in that thin little band there. How far you got to pump it? Well, if you choose your 0 on y to be down here at the South Pole, then that's 2 radii, or 16 to the North Pole, where the hole is, so it'd be 16 minus y. That's how far you had to pump this weight of oil that height. Force times your displacement. So 16 minus y. So there you have it. And this is your delta F times your fixed y, like the second thing they were doing there. So what's your integral? The delta W is going to be the delta F times your y. Okay? And the y, here's, that's, still haven't seen Daniel today. Okay? So, the work then would be the integral of that, and you're going from 0 to 8. Y is equal to 0 to y is equal to 8. Okay? Actually, you're going from 8 to 0, but who cares? I mean, you're pumping the top out first, but it's still going to be the same thing. So going from 0 to 8, that's your delta y, that's your y values. Oh, let's get out front. Sorry, let me back off a little bit here. Got to plan ahead. I didn't. Okay. As usual. the work is equal to, you got 50 pi. That's all in front of this thing. And then you've got your, this thing, y squared minus 16y. And we're going to have the dy out here ultimately. Okay? And then you've got your height that you're lifting it is 16 minus y. Yuck! Okay. So you got to multiply those things too. Okay? Okay. This is going to be a minus y cubed. I know that's going to be there. You're going to have, this will be a 16y squared, and this will be a plus 16y squared, so that's going to be a 32y squared, both plus. Okay, and then finally you have I've got things all crossed up here. Nope, I already did that one. Yeah. I'm not making a smiley face and it's throwing me off. Okay, it's 16y times 16. It's the innards here. Okay, it's really ugly. That's minus 16 times 16 is 256. Okay, and that's a minus 256y. Okay, that's what we're going to be integrating. Okay. And I have left precious little room for that, so let's get it here. The work should equal 50 pi, I can't write for some reason today, 0 to 8, okay, and I'll do 32y squared minus y cubed minus 256y dy, okay. I hope it's all right to erase this next step in case I have to come back and check where I made an error. We won't be able to find it because I erased that. Okay, maybe that's good. Okay, and let's see what we get. I'll do the 50 pi if I can write it. There we go. And what's the antiderivative of 32y squared?
32y to the third over 3.
Perfect. Minus
Minus y to the fourth over 4.
perfect. Minus
Minus 256 y to the second.
over 2. So that's going to bring this down to 128. Okay. Evaluate that from 0 to 8. Okay. Whew, I sure hope this 32y cubed is big enough to get us out of this mess. Okay. Someone with a calculator is going to have to do this part. I'm going to put down the 50 pi because I can write that. Okay. 32 times 8 cubed and divide that by 3. Messy number. Okay. Subtract from that 8 to the 4th divided by 4. Hopefully that's not too big a number. I know it's huge, but hopefully not too big. And subtract from that 128 y squared, or 8 squared, times 64. 128 times 64. I think that's going to give us a negative number, isn't it? I don't know. Doesn't seem like we have enough of a coefficient there to...
That'd be 128 times 8 squared.
Times, yeah, times 64, yeah. H squared, 64.
Yep. We're negative.
That's bad.
Negative 3,754.
So I'm thinking we probably should have done from 8 to 0. Like I said, that would have turned everything over. But let me make sure. What did you say it was? 53,616?
No, sir. It was negative. It was negative 3,754, I think.
Whoa. Okay, I've done something wrong then. Okay. Okay, first I see one thing. When we did the x, doing the x, I said it was y squared minus 16y. They said it's 16y minus y squared.
Wouldn't that still fall out to the same?
Yeah, because you're going, well, let's see. No, that's where the problem came. I said it was 8 minus y. They say it's y minus 8. Now, why do they say that? Okay, I think yuck. Okay. It should, because you're squaring it, not make any difference.
It makes our 32y squared negative.
What's that?
I think it makes our 32y squared negative.
Mm-hmm. Right. But it also changes the sign of one of the others too, I think.
Because it's plus y cubed.
Okay, so circle, so you should have this. Okay, y minus 8. Okay. I haven't quite figured out why, but it gives them the right answer. But it just seems backward to me to say it's but it has to be right. Yeah, that's the difference. And I haven't rationalized it in my head why they say for a circle of radius 8, centered at 0, 8, you have x squared plus y minus 8 squared is equal to that. That's where it comes from. And I think if you reverse those two, everything else does okay. Let's see if that works. Because that's the only difference we have there. So rather than, let's go back up to our integral. Well, let's just everywhere change it. Okay, make this 16 minus y squared. y minus y squared. Okay, that will make this 16y minus y squared. Whoops, wrong thing. All right, Daniel's here. Okay, that makes that one 16y minus y squared. Okay, let me get down here. There you are. All right. Okay. All right. Now, I erase the line that I need now. Yeah. Okay, that is going to be times 16y minus y squared times, what was it, 16 minus y, yeah. I believe that was right. So this would be 256, no. Yeah, that's right, wasn't it? 256 y minus 16y squared minus 32y squared. Okay, because you got two of those. And then you have a plus y cubed. Okay. So basically, these two become plus, and that one becomes a minus. These two are plus, that becomes a minus. Oh, yeah, I could have saved myself a lot of grief because I forgot about my 50 pi. I think we were exactly off by, do you remember the number you came up with that was negative?
It was negative 3,700.
Say that again.
Negative 3,756, I think.
Okay. Now multiply, change that to a plus, multiply it by 50 pi. Times pi.
It is 589,999.
Yeah. Well, pretty close. 589,000. They got 782 foot-pounds. I think they did some rounding somewhere in there. So yes.
I could have been off on my number a little bit.
Yeah. And yeah, okay, it could have been. So guess what? Your I'm not going to do the estimate part, but yeah, we were just off. I shouldn't go through all this. We should have just changed that to a plus, and then I forgot to multiply it by 55. I was thinking, no, that number's way off from what they've got. I forgot we had the 55 out there. So we were right on the money except for the sign. And I think, really, rather than doing the way they did, which I don't think there's a credible reason for doing that, I think what they have to do is go from 0 to 8, and that would have reversed everything. I think what I said was right. They just turned everything around and made it positive. I think what you need to do is integrate from 0 to 8. But pumping from 8 to 0, from 8 to 0, because you're pumping this first and then that and that. So that would have given us the correct answer if we had gone from 8 to 0 rather than 0 to 8. Yeah. Yeah. So I think the way we did it was probably more correct, except what we got by Yeah, if we'd have just changed the size by going 8 to 0 rather than 0 to 8, we'd have had the right answer. And because I don't see how they can say that second one is y minus 8 squared, because the y is generally less than 8, so that would be a negative link there, and it should have been 8 minus y. So I think our way was right. We just should have put the things, limits, reversed order. But let's see how they do it. Maybe they'll explain it better. I don't think they do, but let's see what they do.
Just went through and get our numbers, and then multiply it by 55, got the right answer in the book.
Right, okay. Okay, because you have the increment of force for each disk is given by its weight, that would be that. So it's 50 pounds per cubic foot times the volume. That's where the 50 came from. The volume has a pi x squared times the delta y. That's where the pi came from. The x squared we got for a circle of radius 8 with a center at 0, 8. Okay. You have x squared plus y minus 8 squared is equal to 8 squared. And you see, in my mind, that should be a 8 minus y squared, because the y is something between 0 and 8. Okay, so this is introducing a negative length, and you don't have negative lengths. So I think we were right there. And then this came out then just exactly the opposite of what we did. You can say the force increment is that, and the x squared is that 16y minus y squared, or I said y squared minus 16y. Okay, and then do that, your delta y, goodness gracious, yeah, that's your force increment, delta y, okay, that's the thickness. The area times the thickness is your volume, okay? So note that the disk is y feet from the bottom of the tank, must remove the distance 16 minus y, so that is correct, that's what we used. And so the increment of work is that, the increment force times the distance. And then you put it in, and that's where that. Only thing is we reverse those, and they say, and that's the same numbers we got, but reverse signs. Okay? Now they say, because the tank is half full, y ranges from 0 to 8. And I said that didn't matter. If we had done like we did, the dimensions right, then we should have done 8 to 0. And that would have made everything correct. But this comes out exactly the same answer. So, and you said when you repunched in the numbers, you got exactly the same. So, that many foot-pounds. Now, here's where they do the estimate. To estimate the reasonableness of this result, in example 4, consider the weight of oil in the tank. The total weight is 1/2 the volume of the tank, because that's how much oil you've got. And the volume of the tank is 4/3 pi times the radius cubed. That's the volume of the sphere. So you got half of that, and then multiply that by 50. That's your total weight of the oil in the tank. So lifting an entire half tank of oil 8 feet would be, if you did the entire half tank 8 feet, that would have been this amount of foot-pounds. Because the oil is actually lifted between 8 and 16 feet, then it seems reasonable that the work done is about that. How reasonable is reasonable? Okay, you lifted the whole thing 8 feet, that would only get, you raise this whole thing 8 feet, that would get you up to here. So only that first increment would have gotten, be able to pump out with not much, but all the rest of it. So you would have still the rest of it to pump half the distance. So I don't see, all this estimate tells you is this is a low estimate. It's something greater than that. Yeah, that's greater than that, but it doesn't tell you how close to being that it is. But yeah, it's just reasonable. That's all we're getting there. So that was hardly worth the effort to talk about. Whoa! And they say that is the last example in the section. It is not, okay? So let's go back and do example 5 here. This is lifting a chain. A 20-foot chain weighing 5 pounds per foot is lying coiled on the ground, okay? How much work is required to raise one end of the chain to a height of 20 feet so that it is fully extended, okay? So there's no more coiled on the ground, okay? Now, I sure don't want to draw the picture, but I guess I sort of have to a little bit, okay? So we're going to have little small sections, delta y, because you're lifting them delta y at a time, okay? So there's your small section, okay? And that delta y is in feet. And since the chain is 5 pounds per foot, 5 times delta y would be the length of, the weight of that little section of chain. 5 times delta y. So that's your delta F. That's your force. 5 times delta y. Okay? Now you're lifting that typical section initially on the ground is raised to a height of y. So delta F times y, that would be 50y delta y. Okay? That would be how much work you did. That's your delta W. Okay? Now, you're letting your y, so your W is going to be the integral from, W is going from, y is going from 0 to 20. Okay? 50 is out here. That's not a 50. It's a 5. I thought my delta was a 0 there. 5y delta y. Okay, that's a 5 there. Okay? Sorry. 5y delta dy. Okay? I think we can do that integration, can't we? Okay, what's that?
Y to the 2 over 2.
Yep. Okay, evaluated from 0 to 20. Okay, now make life a little easier. Pull that half out here and make it 5 halves times that. I don't know if that's any easier or not. We'll see. 5 halves, and then 20 squared is 400. Okay, just double the number of zeros when you're squaring. Okay, now this will go into that 200 times, so this will be 1,000 foot-pounds. Okay, let's make sure our units are right. 5 pounds per foot. Yeah, so that would be pounds times y is in feet. Yeah, that should do it. 1,000 foot-pounds. Good for them. Okay? Now, the next one's even worse. Okay? All right. Any questions on that one? That was pretty straightforward. Any questions on it? Yeah or no? Okay. the next one, if there's no questions on that one. The next example, you'll consider the piston of radius r in a cylindrical casing, shown in the figure, which I don't want to draw if I can help it, okay? As the gas in the cylinder expands, the piston moves and work is done. If P represents the pressure of the gas in pounds per square feet, okay? So P equal pressure in pounds per square foot, okay? Usually we talk about PSI, pounds per square inch, but that probably, I don't know why they didn't use that. Okay, against the piston head, V is the volume of the gas in cubic feet. Okay. Then the work increment involved in moving the piston, delta x feet. Okay, I think I've got to draw it here at this point. Here is the cylinder, basically, and here's the piston somewhere in the cylinder, and this is your radius, r. Now that has to be in feet, since they're doing square feet and cubic feet. This is a big piston, okay? Now, the volume in cubic feet would be the area of this piston, which is pi r squared. R would need to be in feet. And the volume increment is times a delta x is how far you've done it. So this is the incremental volume, pi r squared delta x. Okay, so that's your incremental volume. Your pressure in pounds per square foot if you think about this, this is pounds per square feet. If you multiply that times a volume in cubic feet, then you get foot-pounds. So that's where they get that the work done, the delta W, is equal to P times delta V, the pressure times the change in volume. Okay, so the work would then be the integral, and I assume they're saying this is a fixed pressure. That's what I keep looking for. I don't think it's a function of space, so we can pull the pressure outside if it's a constant. I don't know that it is, and that would then be you can pull pi out with it because that's part of that, and that would be r squared dx. But what in the world is your r squared in terms of x? Well, the r squared is a constant too, because the cylinder doesn't change, so pull the r squared out front too. So this is now pi, p, and r squared are all out front. This is bizarre, the way this is turning out. Okay. No. Okay. Wrong assumption. I kept saying, where do they tell you about the pressure? Okay. It's not a constant. Okay. Assuming the pressure of the gas is inversely proportional to its volume, you have that pressure is equal to K over V. There's where it came. So your dW is not, the pressure is not constant. Okay. So what we have now is the work is equal to, I can't read my ugly writing here. Okay, it's pi, and I think the r squared is still just r squared because that isn't changing. Okay, and the interesting thing is they left it in terms of that. K is a constant. Okay, and then they did the integral of dV over V. Okay, without using your dx at all. Okay, so we're going to go back in and figure out what that is, I guess. Well, this is just pi r squared K times, and what's the antiderivative of dV over V? And this is going from V0 to V1. This is just really skirting the issue of the problem in my mind. What is the antiderivative of dV over V?
dV squared over 2V?
Don't think so. This is V to the minus 1 down here. This isn't helpful for integrating it, but if you're trying to do that kind of power rule, what would you wind up with?
V
1, that's in your numerator, and what's in your denominator? In other words, V to the 0 over 0.
Oh, right.
Can't do that. What's the antiderivative of 1 over x dx? Say again? 1 over v dv. dv over v. Foresters harvest.
Trees,
And you call those when you cut them up?
timber, lumber.
And what are the units that you have there that you put onto the truck?
Weight.
Okay, but no, what one of those is called? A 4 foot or an 8 foot or 16 foot?
Board.
Well, you haven't finished them yet. They're still around. Those are?
A log.
Logs! Okay! All right. Now do we got it?
Oh yeah.
Okay, LNV. Okay, so that would be pi r squared times that constant proportionality log of V1 minus log V2, which would be log of V1 over, I'm sorry, V1 over V0. Okay, now, the quantity of gas with an initial volume of 1 cubic foot and a pressure of 500 pounds per square foot expands to a volume of 2 cubic feet. Find the work done, assume the pressure is inversely proportional to the volume. Okay, what a pain in the neck this is. So the pressure at 1 cubic foot is equal to 500 pounds per square foot. This is such a weird unit. Pounds per square foot. Okay? It expands to 2 cubic feet. So the pressure at 2 cubic feet, we don't know what that is, okay? But our assumption is that the pressure is equal to K over V, and at 500, at 1 cubic foot of volume, that would be 500 over 1, so the K would be 500. So K is equal to 500. Okay. So put this in as a 500 here. Pi r squared times 500, so 500 pi r squared times the log of 2 over 1, so log 2, okay? Now I missed something here. Oh yeah, sorry. The pi r squared is the area, so I mean that's taken, okay, sorry about this. You don't need that in there because the volume is just V, sorry. They just screwed up the whole problem here. Rather than trying to figure it out, it's just pressure times volume. You don't need to use the radius, you don't need to use any of that. It's pressure times volume. And it's a dV, so it came up just 500 times the log of 2, basically. And do 500 times log 2 and what you get. Why they gave us all that information that we didn't use, I'm not sure.
Yeah, that's it, 346.6.
346.6, exactly. Okay. Sorry about that. No wonder they left it off the slide set. It was just a ridiculous sort of problem. Homework exercises here, 7.5. Do either 5 or 7. They're both at Calc Chat. 7's at Calc View. Then do any of the odds, 9 through 13. They're all at Calc Chat. 11's at Calc View. Then do any of the odds 15 through either 15 or 17 if you're interested in propulsion. They're both at Calc Chat. 19 to 25 if you're interested in pumping water. They're all at Calc Chat. Do 27 if you're interested in pumping gasoline. That's at Calc Chat. 29 or 31 if you're winding a chain. Those are both at Calc Chat. 29's at Calc View. If you're lifting a chain, then do 33. And you could think about doing 35 if you'd like, and then 37 and or 39 if you'd like to do one of those. Ordering forces, I'm not sure what they mean by that, but you can give it a shot. It should be at Calc Chat. 43 should be at Calc Chat and Calc View. That's Boyle's Law. Hydraulic press, either 45 or 47. They're both at Calc Chat. 49 is modeling some data. And then there's a pyramid at Khufu, or whatever that is. I'm sure it's somewhere in Giza, in Italy, in Egypt, I'm sorry. Phew, goodness gracious, what a pain. All right, we already had finished example 4, and it got to the end of the section. Let's now get out of that section and do section 7.6. Now, just because most of you are going to be engineers, is that right? Okay. I'm sure you're going to be dealing with moments. Okay, so I think probably we should cover this. I'd kind of like to skip this one, but I'm sure you're going to need it. So let's do this one. Application of integration. Now we're going to talk about 7.6. Moments, centers of mass, and centroids. Okay. Our objectives here are first to understand what we mean by the definition of mass, and find, I think they mean the definition of center of mass, but they mean mass. Find the center of mass of a one-dimensional system, which is pretty straightforward. Center of mass of a two-dimensional system, which again is not so awful, but then find the center of mass of a planar lamina, which we've got to figure out what in the world that is, but that's actually easier than this. And we'll use the theorem for Pappus, which is a pretty interesting thing, to find the volume of a solid of revolution. So, is there any more? No. So we'll start with mass, okay? Several important applications of integration are related to mass, okay? Mass is a measure of a body's resistance to changes in motion, which basically is, another way of saying that, is a measure of a body's inertia. Okay, if you like that term better. And it's independent of the particular gravitational system in which the body is located. So most bodies we deal with are in our gravitational system, so we treat mass as if it's equivalent to weight. It's not, okay? But in our system where we live, it is equivalent to weight because of the constant gravitational field. However, because so many applications involving mass occur on Earth's surface, the object's mass is sometimes equated with its weight, which is not true. It's not technically correct, but weight is a type of a force, and as such is dependent on the gravitational force. Pull. Force and mass are related by this equation. Force is equal to mass times the acceleration due to gravity. Okay? Well, any acceleration, but if you're talking about weight, if this was weight, it's mass times acceleration due to gravity, whichever gravitational field you're in. But a force in general is always the mass times acceleration. Now that's talking about a net force on an object, not any individual force. Okay. Table below lists some of the commonly used measures of mass and force together with the conversion factors, which is totally unnecessary, but I appreciate you trying to cover this. Okay. How many of you ever gone to the store to buy a slug of potatoes? Never. Okay. We never use this term, but that is officially the U.S. term for mass. We don't use it. It's not used. We measure the weight, which is in pounds, which is a slug foot per second squared, which is the only way we ever get a slug is to take the weight of it in pounds and divide by the feet per second squared. That tells you how many slugs you've got. Okay. The international, this SI, they should say, that's a kilogram, and is the mass. Newton is the measure of force. That's the kilogram meter per second squared. In the CGS system, which we don't really use that much anymore, mass is in grams, and then your force would be in dynes, which is a gram centimeter per second squared, which is hardly ever used anymore. So why go through this? Now here are some of the conversions that are legitimate. Pounds and newtons, they both measure forces. 1 pound is 4.4442 newtons. In fact, just a little less than 4.5 newtons. So a pound is a heavier measure than a newton. A newton is less than a quarter of what a pound is. Okay? And a newton is less than a quarter of a pound. A dyne, goodness gracious, who cares? But you move the decimal, and I don't know if you want to fiddle with this or not, but you get from here to here is 10 to the minus 3, or go from here to here is 10 to the third. You get from here to here is 10 squared, so it's 10 to the 5th. So take your decimal and move it 5 places. From here, 1, 2, 3, 4, 5. So that's how you make that conversion. Why in the world would you even mention this? That's such a tiny number. Who cares? But even more so, why would you say how many ounces it is? That would at least be a little more reasonable number, but they don't do it. And a dyne would be 10 to the minus 15. Now, going back here, a kilogram, a slug, is more than 14.5 kilograms. Kilograms is a pretty hefty measure. This book, I don't know, it may be 2 kilograms. So this would be, it would take 7 or 8 of these books to make one slug. That's a pretty heavy slug. I hope he's not in my garden. No, that's not the same thing. Okay? Or a kilogram is just a small fraction of a slug. A gram is an incredibly small fraction of a slug. That's just 3 more decimal places on that. And then, why is this thrown in here? A foot is 0.304 meters. A little less than a third of a meter. I don't know why they put them in here, but maybe there's a reason somewhere. Okay, find the mass. Oh, no, I can't believe they're asking us to find mass and slugs of an object whose weight at sea level is 1 pound. Okay. Okay. Here's the deal, folks. Who cares is my first answer. But let's actually do it, okay? 1 pound is equal to 1 slug, and there's no abbreviation for slug, times 1 foot per second squared. Okay. Now, okay. Now the weight at sea level is 1 pound. Now it can't be that easy. Okay, yeah, I didn't think it could be. Let's go back. No, okay, here's what's confusing about this. Hey. You just in here to see me later? Okay. How are we doing on time?
30 minutes.
Yeah. We're still in class for another 30 minutes.
My class will start and I know what
I'm sorry, I can't hear.
Oh, my fault.
What you say? Your class?
I was saying my class and it started to get eaten, so I was just saying that.
Okay. You're just hanging out in here? Okay, that's fine. Okay. But we're going to continue with class. But were you here to see me? Or you're not?
I was.
Oh.
I wanted to discuss when I was going to get a grade.
It's what?
When I was going to get a grade, because it's not a blackboard.
Okay. All right. So, are you just going to wait till this class is over? Okay. Right. Okay. Okay. All right. All right. This slide here is a little misleading. Okay. Okay. These are units. Okay. A pound is a force unit, and that is slug feet per second squared. Okay. A newton is a kilogram meter per second squared. A dyne is a gram centimeter per second squared. That's all that's saying. Okay. Now, when it's said, and this is what's okay, what they're asking for here, a weight of 1 pound, okay, the acceleration due to gravity in the U.S. customary units is 32 feet per second squared. Okay? Now, then what? Okay. This is mass. This is acceleration. Okay? So if we were looking for mass, which is what we're looking for, how many slugs, mass is equal to force divided by acceleration. Okay? The force here is 1 pound of force. Okay? And that pound is slug feet per second squared. Wait, slug feet per second squared. Okay. That's what a pound is. A slug foot per second squared. Okay. Divided by the acceleration due to gravity in the U.S. customary system is 32 feet per second squared. So the feet per second squared goes out. So this gives you, okay, I just rewrote pounds instead of feet per second squared, because that's just a unit thing there. So the mass would then be 1/32 of a slug, which is 0.0, gives it in the book, no, 0.03125 slugs. Remember, a slug is a very small, a very large unit, so it doesn't take many slugs to make a pound. Because when you multiply the mass times the acceleration due to gravity, you should get the force, or the weight, and that would be 1 pound. So that's what they're getting at here. That was just your units, okay? So 1 pound would be 1 slug at 1 foot per second squared, but your gravity is 32 feet per second squared, so you would, to multiply that, the acceleration by 32, you have to divide the mass of that to get 1 pound. So it's a strange thing. Who cares? Because many applications involving mass occur on the Earth's surface, this amount is called a pound mass. They don't even call it a slug. They call it a pound mass, which is a strange unit in itself. So I'm not really sure why they went into that. It seems totally unnecessary. But let's clear it and see how they say it, which is pretty much the same thing I think I did. This author gets a little carried away, it seems like. Using 32 feet per second squared as the acceleration due to gravity, mass is force divided by acceleration. So if you have 1 pound of force or weight divided by 32 feet per second squared, you get 0.03125 pounds per foot per second squared, or slugs. Okay. Blah, blah, blah. What's that?
I guess he's making sure you get your money's worth.
I guess so. I see no purpose in even bringing this kind of stuff up. No one uses it, okay?
So where did the metric term slugs come from?
For what?
Slugs, the main.
I really don't know. No one uses it. It's just, I guess they needed to name mass some unit and say, well, how about a slug or something? I don't know. That's my best guess.
Anything to do with a slug, like a bullet? Okay.
Oh, I hadn't thought of that. I thought of that little slimy thing that you get in your plants in the garden. That wouldn't be that, because that, okay, so I don't know. I really do not know. Okay? I have no clue. No one uses it. No one worries about it. This is the most I've ever seen written about a slug. Okay. So let's go to the center of mass in a one-dimensional system. What do we mean by that? Don't worry about slugs. Okay. I hope anyway. We'll now consider 2 types of moments of mass. The moment about a point and the moment about a line. Okay? To define those 2 moments, consider an idealized situation in which mass m is concentrated at a given point. If x is the distance between that point mass and another point P, then the moment of mass about the point P is the mass times its the distance, okay? Where x is the length of the moment arm, okay? Now, to put this in a little more practical terms, I think of it this way. I'm trying to shovel up something, just to make it good and gross, dog poop, okay? Now, I don't want to get any closer to that dog poop than I have to get, okay? So I get as long an arm of a shovel as I can find. And I don't know how much is out there, but it's a pretty good pile, so it has certain mass. I'm going to take that long shovel and try to lift it. Now, I'm going to have to do a lot more lifting because my fulcrum is here and my thing here. I'm going to have to exert quite a moment to pick up because it's the mass of it times the length of the moment arm. The longer that length, the more the greater the moment. Okay? That's a pretty gross example, but sort of get what we're talking about. That is a point mass about the moment about a point. Okay? Now, that concept of moment can be demonstrated by a simple seesaw. Okay? Or any lever, by the way, which a shovel is a type of lever. A child of mass 2 kilograms sits 2 meters to the left of the fulcrum P, and an older child of mass 30 kilograms sits 2 meters to the right of P. What's going to happen?
The kid on the right's going down.
Yeah, the kid on the right's going down, and the kid on the left's going up. Nothing can do unless the kid on the right pushes up, then they can seesaw. If not, poor little kid just hangs up there, which you used to do to your brother, didn't you? Okay, never mind. We won't answer that question. Okay. From experience, you know the seesaw will begin to rotate clockwise. Okay, because the guy going down is like this, moving the larger child down. The seesaw will balance when the left and right moments are equal. They're not ever going to be equal the way they set up this problem. Okay, so what you do to make them equal is bring this kid closer, this kid further, because now the moment about that point, 20 times something has to equal 30 times something. Okay, and you've got a total of 4 feet there. Let's let the first something, let's this be 30 times x will be 20 times 4 minus x. Okay, when those are equal, then you would have the cut. And you used to do this. Remember, maybe y'all didn't. On our old playgrounds, we had the seesaws there, but they had a series of little humps under them. Yes, and you could adjust your board so that it would be in between 2 of the humps. I always was on the short end because I was always the heaviest one in the class. Okay, up until high school, and everybody passed me. Okay, on the football team anyway. Okay. This rotation occurs because the moment produced by the child on the left is less than the moment produced by the child on the right. The child on the left had 20 times 2, which would be 40 kilogram meters. So on the right was 30 times 2, which is 60 kilogram meters. So it went down. To balance the seesaw, the 2 moments must be equal. For example, if the larger child moved to position 4/3 of the meter from the fulcrum to a position 4/3, okay, from the fulcrum, then the seesaw would balance because each child would now produce a moment of 40 kilograms per meter. Oh, okay, I see what they say. The larger child moved not from 2 meters away, but 4/3 of a meter away. Okay, so if this was 30 times 4/3, 3 will go into 30, 10 times, 10 times. No, 4/3. 3 will go into that, and this would be a 4 in the numerator. Yeah, 4, that would be 40, and that would be. The other child stays the same place. I was moving the whole seesaw. They were just moving the kids. Okay. Here's what they were saying. Move this kid up here to about right there, and now they'll be balanced. Okay. I was moving the whole board, keeping the kids in the same place. Okay. Either one of them works. Okay. you can introduce a coordinate line on which the origin corresponds to the fulcrum, as shown here, and several point masses are located on the x-axis. The measure of the tendency of this system to rotate about its origin is the moment about the origin, which of course is at the fulcrum. And that's the tendency to rotate. It's defined as the sum of the end products m sub I times x sub I. Okay? Now, what you have to have here, if this is your zero here, these x's are negative. These x's are positive. The m's are all positive. You can't have negative mass. They're all positive masses. Okay?
Yes.
Thank you. And if you had a finite number of objects, finite point masses here, then M1 times X1, which is, we know in this is a negative number, plus M2 times X2, which you know X2 is a negative number. That gives you some negative sum. Over here you have M3 times X3, which we know is a positive number, and M sub n minus 1 times X sub n minus 1, which is a positive number, plus M sub n over times X sub n. Add all those up, and there's a bunch more in there, you know. Add all n of them up. If that's equal to 0, the system's in equilibrium, it will be balanced. It won't be tipping one way or another. It won't be trying to rotate. Because moment measures that sense of rotation, the tendency to rotate. And if they're balanced, that's 0. Okay, so if the moment is 0, it's an equilibrium, it won't tend to rotate at all. So think of mass as a tendency to resist inertia, okay, change of position in any sense. Well, moment is a tendency to resist rotation, okay, so to speak, especially about a point. Okay. Now, the moment about the origin is denoted as m sub 0 and can be written as m sub 0 is the summation of all those moments. Okay, if m sub 0 is 0, then the system will be in equilibrium. That's just saying the same thing we did here. Moment about the origin. They're just substituting that phrase there to be m sub 0. Moment about the origin. For some reason they make that capital M and the others, well, because that's a moment, not a mass. The masses are little m's. Okay.
Could you use moment in a sentence?
I will in a moment, but not now. No, I'm just kidding. Trying to think of one that would be sort of practical. Kind of imagine flying a plane at a certain altitude, and you're a bomber, okay? And you've got your whole wings here loaded with bombs, okay? And you decide to release a whole bunch of them over on this wing and not on this wing. Your moment would be altered so that you're tending to go down like that. Yeah, and then you have to adjust all your ailerons and other things to maintain level flight. Okay, that would be probably pretty silly, but you know that would illustrate what a moment is. The moment would be out of balance or whatever. Yeah, I don't know. Were you gonna say something?
Yeah, I was comparing it to like the center of gravity.
Yeah, and that's exactly what we're getting to. You're right on the money. What we're going to be talking about next is center of gravity. Okay, this back here, they said another thing here. No, I saw it. Yes. X is called the length of the moment arm. And there are some instances that's called the writing arm, not writing like this, but that writes itself, and you see that. So wherever, like I said, the plane had to right itself to get back in level flight by adjusting the flaps and things like this, having one go up and one go down. That would be adjusting the writing arm, which is also the moment arm. That would be the same type of concept. Okay, so when you said center of mass, that's usually associated with substances writing arm or moment arm. Okay. Now, for a system that is not in equilibrium, the center of mass, here you nailed it, is defined as a point x bar at which the fulcrum could be relocated to obtain equilibrium. That's what I was doing with the kids on the seesaw, is not moving a kid, but moving the fulcrum, okay, on the board, over the fulcrum, to attain equilibrium. If the system were translated x bar units, which is that center of mass, then each coordinate would then become x minus x bar, okay, because the moment of the translated system would then be 0, okay? So think of this as each moment, each mass, each position of the mass, writing arm, moment arm, okay, of this m sub I times s sub I, so 1, 2, 3, 4. But then you're going to subtract off that center of mass, wherever the center is. That would be summation. This is all your, that's your entire moment, okay, you might think of, minus just the moment of the center of mass, and that is equal to 0, meaning these two things are equal. Solving for x bar, that would be the summation of all your moments divided by the total mass, which is exactly what that is, because this is a constant. You can pull this outside. So this is exactly how you get the center of mass of the system. It's the moment of the system about the origin divided by the total mass. The moment is the summation of all the masses times their distances from the center. So when m1 x1 plus m2 x2 plus all those is equal to 0, the system is at equilibrium because all this is at 0, then your center of mass is 0. You're at your center of mass. Now, I don't know if this is helpful or not. I never got to see the guy, but I heard about him a lot. When we were in grammar school, there was an Olympics that happened either before we were there or while we were there or something. And a guy from just down a couple counties away in Georgia named Paul Anderson won the Olympic heavy weightlifting thing. He was the Olympic champion. And he came home and set up a foundation and worked with kids and stuff. He was a strong guy, big old heavy guy too, but most of the weightlifters are, And they said he would go to speak, motivational speak at grammar schools, and he had this platform that he carried with him, and he would have it up on some sawhorses, fairly tall ones and stuff, set up, have the whole class get up on the platform. Now, that was a pretty heavy thing itself. And he would get under the platform and lift the entire class, platform and the whole class of kids, and lift them. He was one strong dude, okay? And the whole purpose of it was he had to be at the center of mass, else he would have knocked the kids over. And so he said, you have to remain centered. He used this as a motivational thing. Kids just got a jolt out of being lifted off the ground, you know, by one guy, you know. I never got to experience that.
How many people was it?
It was small classes, I'm sure. And it wasn't the teachers, just the kids. So if he could lift the platform, probably all the kids didn't have a lot more weight. You know. So, yeah, to hear people talk about it, I thought, wow, okay. I never got to see it, but that's what they said. So here's what we got. Moment and center of mass, one-dimensional system. At the moment, the point masses M1, M2, M3, up to Mn, be located at these various places, x1, x2, x3. Now these are all on a line, remember, one-dimensional system. They're not scattered all over the floor like the kids would be, one-dimensional system. The moment about the origin then would be M sub 0, and that would be the summation of all these. M1 to x1 to the other. All these moments. Just add it up. Okay? The center of masses then, x bar would be that moment divided by the total mass, where M is M1 plus M2. All these masses added together. Okay? That's what we define the center of mass of a linear system. Pretty straightforward. Calculate the moments first, divide by the total mass. That's your center of mass. Okay. Now remember, moments in a sense have a dimension to them. Okay. So you have to sort of keep that in mind. So here, let's do one. Find the center of mass of this linear system shown here. Okay. Now, the odds are it's probably not going to be here. Okay, I would guess it's not anyway. Okay, so let's do the center of masses. Okay, what would be the moment of the first one? Numbers in here are the masses. Anyone? Mass is 10. Its displacement is minus 5. That would be negative 50. Plus 0. Plus 20. Plus 70. So this would be M sub 0. This total of those. And what would that be? Second? Okay. 70 and 20 are 90. Right? Minus 50 is 40. Okay. 40. What's the total mass? I guess that's little m. I like to use capital M, but I believe the book is using little m. Oops, I already got the equal sign there. Okay. What's that? Total mass.
40.
Okay. Yeah. 20, 30, 40. Okay. So what's the center of mass? X bar. 1. Okay. In other words, if you move the fulcrum here, now the moment should be 0. This would be 15 times 1 now, right? That would be 15, minus 15. This would now be minus 60. This over here would be 15, and that would be plus 60. Sure enough, that would be exactly where the center of mass would be. Do you see that? Okay. So the X bar is a dimension, as in distance measure, okay? It would be 1 unit, whatever your units are, meters, inches, furlongs, whatever, there. Okay. All right, so that's example 2. Okay. Now, let's see what they do. Oh, let's erase it and see how they did it. Should be about the same. I just did it pretty helter-skelter. But they did, 10 times -5 plus 15 times 0, did that. That came up with 40. The moment about the origin, the total mass is little m, which is 40, so the center of mass would be +1, which would be 1 unit to the right. Notice that the point masses will be in equilibrium when the fulcrum is located at x = 1. And sure enough, we showed that. All right. Now, rather than defining the moment of a mass, okay, you could define the moment with a force. In this context, the center of mass is called the center of gravity. So no longer masses, but weights. Okay? When they say force, think weight. Consider the system point masses, M1, M2, M3, up to Mn, located x1, x2, up to xn. Then because the force is the mass times acceleration, remember? Okay? And if we're talking about weight, then we're talking about acceleration due to gravity, whichever system of units you happen to be. The total force on the system would be M1 times A, and the whole system is moving at the same acceleration, so it would be all that, so it would be the total force, mass of the system times the acceleration of the system, which is exactly what net force is. Okay. Now, if these are little forces of different accelerations, then this would still work, and the total mass would be that. Are we out of time? Oh, unfortunately we are, aren't we? Okay, sorry. Where are we here? We haven't quite gotten to torque, so we will pick up there at the beginning of torque. Let's see if we've done enough for you to do any homework exercises. We should have done enough for a few anyway. So let's see what we got. I think you can do 5 or 7. They're both at Calc Chat. 7's at Calc View. I think you can do 9. That's the Calc Chat as well. And then we'll hold off and do the 2-dimensional later. Okay. So not many, but just a few to work on. All right, good deal. Yes.